So we've been obviously talking about kinetics, and let's see here. We talked about a number of things involving kinetics, and again, kinetics being about really sort of the rate of a reaction, how fast or I guess how slow a reaction takes place. We started off talking about sort of the rate expression, which really does sort of relate the entire reaction, how the reactants are changing over a period of time, how the concentration of the products are sort of appearing over a rate of time. Um, and remember that we really just need one piece of information in terms of the rate expression. We do take the coefficients into account, so we get something that looks like this, that the rate is equal to, say, minus 1 over 2, change in the concentration of A over the change in time. Again, if our reaction, for example, had a coefficient of 2, therefore RA, that again does take into really the multiple relationship. It does give us that sort of change in concentration over time, which is basically molarity over seconds. A lot of the instances, remember, as we talked about in sort of the rate expression aspect of it, we would expect obviously the reactants to be decreasing with time. So they should be changing sort of negatively, while the products should be obviously increasing with time. So they should be changing sort of positively. And remember, when we do a sort of rate expression, so I just scribble over the page here. There we go. When we do the rate expressions, our average rate for the reaction should end up being a positive number. So that's why, for example, this guy would be negative, 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 gives you a positive. On the product side, if we had a product here, say 2B, again, the rate is equal to basically 1 over 2 change in concentration of B over the change in time. Here it's positive, as again, as I mentioned, we should think that it will be increasing with time. And that again gives us our sort of positive average rate for the reaction. We could use this, obviously, like I mentioned, to really just figure out how everybody here is sort of changing with time. That's not to be confused with sort of the rate law, which really does just focus in on, for example, reactants. And this is what the rate law, for example, looks like if you have like A plus B goes to C. And here it's really just about the reactants. Here's our rate constant, which is sort of like how fast it's sort of happening. Remember here, these are our orders. And orders, as we sort of spoke about earlier, again, is sort of the proportion that you need of those, say, reactants to basically kind of sustain a specific rate. You also can use the orders and the rate law to figure out, if you want to, say, speed up a reaction, you could maybe increase one reactant versus another. If you want to decrease a reaction as well, you could actually cut back, obviously, on one of the reactants versus the other. Again, if you just had, say, a generic sort of the rate equals K A to the 1, and again, usually write the 1, but B to the 2 here. Again, if we start out with, say, 2 molar of each of these guys and kind of put it into here, we would get basically 4 times 2, which would be 8. Again, assuming this is constant, so we don't have to think about it. So, if we wanted to kind of increase the rate of this reaction, we could just maybe double the concentration there of B. And when we do that, we get 4 times 4, which is 16 times 2, which would be 32. So in this sort of arrangement, we could obviously make the reaction maybe increase fourfold by just simply increasing the amount of B that we started with again. So knowing sort of the rate law, the orders, how the sort of the proportion is as they react allows you, again, you can sort of manipulate that reaction. And why would you want to do that? Maybe in a situation like we might have talked about as well, maybe you're trying to actually run an experiment and it's just happening way too fast for you to record information. You may want to sort of slow down the reaction so you could actually get some data and information like that. So sometimes that's a useful sort of thing. Remember that we do find all these guys sort of experimentally. So in this case, we usually do some type of calculation like rate 2 over rate 1 is equal to K times A to the X, B to the Y. And remember that we basically go to a table, which is a very common thing in kinetics given to you, concentrations, initial rates, and those type of things. and we basically substitute those in. We try to pick two entries from the table where one of the concentrations remains constant, the other one varies, and that will allow us really to get something like we've seen in the past, like hey, 4 equals 2x or something like that. And we can obviously figure out, x is equal to 2 or something like that. Again, you can take the natural log of both sides and divide if you need to, if they're not really pretty whole numbers. Sometimes you can get nicer-ish whole number-ish if you kind of go with the larger rate on top, all that information. And that usually will kind of give you more sort of whole numbers. You don't have to do that, but you just will probably get some decimal numbers if you kind of do it the other way. Smaller guy up on top, obviously, versus larger guy on the bottom. So again, we talked about this, so you can use that information to figure out the orders. Once you do that, you then can use the completed rate law once you have the orders to really figure out what the value of the rate constant is at that point. And that led us into, I think, sort of where we finished up last time, which was talking about some different orders of reactions. We talked about kind of first order reaction. Oops. Right, there we go. First order reaction, second order, and zero order. And again, these are the sort of common orders of reactions that we usually come across. We sort of, I think, touched upon this as well last time. Most of the time when you think about sort of a chemical reaction that you've seen or a chemical equation that you've seen, for the most part, you typically see perhaps one reactant, two reactants, occasionally three reactants. You don't really see a lot more than, say, three reactants usually. Most of the time it's two or less. And, that really leads to these guys being sort of the common orders that you usually will sort of end up with. We don't usually get too much third order, fourth order, fifth order, and all those type of reactions. Again, in order to kind of generate that, you most likely would need a lot more reactants sort of reacting to give each of them sort of an order and stuff like that. So these, again, are sort of the common ones. We saw some graphs that go with each of these. And remember that our first order graph is the natural log of A versus time, should yield you a straight line with a negative slope, where the slope of that line will equal negative k. So not k, but negative k, again, giving us our rate constant that will become positive. Our second order, which is really kind of the only positive sloping line that we saw, 1 over the concentration of A versus time, again, yielding us a straight line in the positive direction. Here, the slope will equal k. And our zero order being the concentration of A versus time, also yielding you that negatively sloped line. And again, the slope would equal minus k. And again, these are the three sort of common graphs that we associate with those orders: first order, second order, and zero order. And obviously, if you were doing more of a graphical approach, you would look for whichever one obviously was the most linear sort of straight line. And you could use the slope, obviously, to figure out the rate constant. Any questions on anything we were talking about here so far? Okay, so let's move a couple things out of the way here. So this just also summarized some of the other important information that we talked about for each of those orders there. There's those sort of integrated rate laws, basically concentration and time sort of equations. And there are different depending on the orders. So this again is our zero order one, which is basically the concentration equals the initial concentration minus KT. Again, you can think of this as sort of your final concentration. This is your initial concentration. Obviously, K here is your rate constant. And a reminder that T here is time, not temperature. Remember that they do have different sort of half-life equations. So remember that for a zero order, the half-life is the initial concentration divided by 2K. So the initial concentration does play a role in terms of sort of the half-life. Remember that the half-life is the time it takes for half of whatever you started with basically to go away. So obviously, if you just think mathematically about this, the larger the initial concentration, right, the longer the half-life is going to be in that particular case of zero. Kind of big number divided by a smaller number gets you a larger number. For our first order, natural log of A equals natural log of A naught minus KT, and that is the half-life equation of natural log of 2 divided by K, which is the rate constant. The natural log of 2 is that sometimes you'll just see the 0.693 number. That is basically what the natural log of 2 is. And for second order there, 1 over the final concentration equals 1 over the initial concentration plus KT. Again, here we see initial concentration into account for our second order in terms of the half-life. Here, though, if you just think about it in a mathematical sort of approach, it's on the denominator there. So larger the initial concentration here, kind of the smaller the half-life are going to be, because you'll have a bigger number on the bottom versus top. And again, that will affect, again, the sort of half-life that you would expect to see. So obviously, this is a good slide. It kind of summarizes all those important sort of equations that you need, along with those graphs that you need to know. Remember that, again, those graphs really do come from rearranging these concentration versus time equations. And if we look at those graphs, we want to kind of determine, come back here, thank you. We kind of want to determine which one is more linear. And we sometimes can do this in an experiment if you're not sure what the order is. You basically can prepare each of those graphs, all three of those graphs that we were just talking about on the other slide, which is our, again, natural log of A versus time, our concentration of A versus time, and our 1 over A versus time. And again, this being our first, 0, and second order graph. And remember that these really do come from rearranging those sort of equations. This would be like the natural log of A is equal to natural minus KT plus the natural log of A. That's Y is equal to mx plus B. Same thing with this guy here. That would be the concentration of A equals minus KT plus A naught. And again, this would be Y is equal to mx plus B, and same thing with our other guy. How would we determine, which one's more linear? Just like when you use Excel, for example, you could look at the R squared value, right? R squared value closest to 1 indicates that it's a pretty linear relationship or perfect linear relationship. And that will help you determine the reaction order by graphing. Again, if the concentration versus time, then it would definitely be 0 order. First order, if it was this guy, more linear, and obviously second order if this guy was more linear. Any questions on orders or anything like that? So now what we're going to talk about then is sort of the relationship between temperature, energy, and reaction sort of rate, and some important factors that, do affect, oops, good talk. Let's talk a little bit longer about that. Do kind of affect the reaction sort of rate. So if we look at two sort of energy diagrams, these are, again, energy level diagrams. We have our reactants, we have our products. First off, when we look at an energy diagram such as this, we see our reactants here on the left are higher in energy than our products. So in order for those kind of reactants to get down to products, overall energy has to be given off. Thus, it is an exothermic reaction. Remember that an exothermic reaction means that the delta H value should be negative in that particular case. So whenever you look at a diagram like this, again, reactant is always higher in energy than products. That always is an exothermic reaction. And we see sort of the opposite happening here. Our reactants are lower in energy than our products in this particular reaction, which means heat and energy, or energy, needs to be put in, are absorbed. And that obviously means it's an endothermic reaction. Remember, endothermic means delta H is going to be positive in this particular case. So what really kind of determines how fast a reaction really will take place is this area here between where the reactants are to sort of the peak in energy that occurs as this reaction is basically taking place. And in both of these cases here, again, from the reactants to sort of that peak of the energy hill, that is what is basically known as the activation energy. So the activation energy, which is E of A, is the minimum amount of energy that's required for a reaction to really take place. Now, just because things sort of collide in each other or with each other doesn't necessarily mean that products will be formed. Um, there's actually a couple of important things that need to sort of happen. They do need to kind of come in contact with each other. They do need to come in contact with each other in sort of the right orientation, sort of the active side, if you want to think about it at that point. And they do need to sort of come in contact with each other, possessing the right amount of energy for that reaction to take place, you know, sort of the hill here. So you can kind of see in this thing, this is the hill that the reactants need to climb basically to get to the other side. And same thing here, the hill that they have to climb to basically get to the other side. That's your activation energy. We see also a couple of things just from these two diagrams here. We definitely see that in an endothermic reaction, the activation energy is the hill it has to climb to get to the other side is much larger than our exothermic reaction, right? That's also why maybe it's endothermic. I put some energy in there to make sure people have enough energy to get up and over the hill to the other side, versus here, there's sort of an excess of energy, you don't need as much. What happens when we get to the sort of very top of the hill here on both of them? We get this guy in the middle, and this guy in the middle is what is sometimes referred to as a transition state complex, or sometimes referred to as a activated complex. It is basically an intermediate in this reaction as our reactants go to products. So what do I mean by that? Well, typically speaking, as this reaction starts to proceed, basically what we need to do is to start breaking some bonds, right? We need to like kind of start breaking bonds. And as the reaction starts, we're going to start breaking these bonds. It's going to kind of work its way up the hill, going to start breaking bonds. At some point, it's going to also need to start making some bonds here as we kind of proceed up the hill. So first you got to break some of those bonds. Obviously, you got to start making some bonds as we roll up this hill till we get to sort of the peak in energy up here. And this is again our transition state, which is the top of the hill, our transition state complex. And what we know about something that's right there at the peak of high energy, it is usually something that is very unstable, right? Because in chemistry, things don't like to be very high in energy, right? Things are always looking to be sort of in the lowest state of energy. And that's what it's sort of going for here in this particular situation. So, what it usually ends up happening is relatively quickly at that point, this little intermediate then kind of rolls down the hill to our products as we go there. This activated complex usually is sort of a species that has partially broken bonds and partially made bonds. So it's very sort of high in energy. You got these guys sort of simultaneously breaking apart and finding new bonds to reform, sort of happening at the very top there. And then it will sort of go off to the other side relatively quickly. That's why it's usually, in a lot of cases, very hard to isolate that sort of transition state complex because it's very high in energy, got those partially made and broken bonds. It makes it very hard in a lot of reactions to sort of isolate those things because they really don't hang around for a very long time. Now, again, that whole sort of transition that's occurring is responsible for sort of the bonds that are making and breaking. And again, that kind of quick transition, if you will, as you come down the hill. So what does all this has to do sort of with the rate of reaction? Well, obviously, if you have to walk up a hill and you have a very big hill to climb in terms of activation energy, it's probably going to take you much longer to reach the other side than if you had sort of a smaller hill to climb. And that has obviously a direct effect on sort of the rate of the reaction. Under certain conditions, maybe there is only a certain amount of molecules that have sufficient energy to get up and over the hill to get to the other side. Same thing here, sufficient amount of molecules here have enough energy really to get up and over to the other side. That's why when we talk about sort of speeding up a reaction, right, one way we can speed up a reaction is to increase the temperature typically. When we go about increasing the temperature, what are we really doing to all these guys that we're starting with? We're giving them a lot more energy, which means that we end up with sort of a greater proportion of molecules that actually do have that sufficient amount of energy to get up and over to the other side. And that's why we typically obviously will see a increase in the rate of the reaction when we increase the temperature, again because they have now gained enough energy really to hop over the hill. Like you got a nice boost and you decided to run over the hill rather than kind of walk over the hill, right? It's going to get you onto the other side a lot quicker. Opposite is true as well. Obviously, if we kind of cool down the reaction or take out some heat and energy, we're now really lowering the sort of amount of molecules that have sufficient amount of energy really to get up and over that hill. We're going to see that reaction, typically speaking, sort of slow down. Any questions on?
Yeah, I had a quick question about that. So are you saying that if the activation of energy was increased, then it would also affect the rate of energy?
If you had a much, for example, we just look at these two sort of pictures here. The reaction on the right, you would anticipate probably under sort of the same conditions, perhaps would take a lot longer for that reaction to take place. Again, you can just see the barrier to get to the other side is much larger than the hill on the left. So there is a direct relationship or correlation to how big that sort of activation energy is to how fast a reaction can occur. And again, sort of the bigger that hill, it's going to just take longer to get up and over the other side. Going to require a certain amount of more energy to get up and over to the other side. And under sort of normal conditions, for example, just think normal temperatures and sort of those type of conditions, there's really only going to be sort of a certain proportion of molecules that really do have enough energy to get up and over to the other side. Um, and again, so just in direct comparison, sort of hills, the smaller the hill you would have, the faster you would expect the reaction to occur because there should be probably a greater proportion of molecules that have that much energy to get over. But if you then move the hill like way higher, there's going to be less of those guys are going to be able to make it over as quickly, and it's going to take longer for them to kind of reach the other side. And that's why temperature plays an important role in terms of the speed of the reaction, because really when we play with temperature, we're really just either kind of increasing energy or kind of decreasing energy, and that will have an effect on sort of the rate of the reaction. Other questions on
Thank you.
that? Welcome. And we'll talk about it here towards the end as well, but that's sort of how a catalyst works. Catalyst finds sort of an alternative path, and what it's able to do is actually lower that hill, that activation energy. And by lowering that activation energy, we also see sort of an increase in the rate of the reaction. Again, they don't have to go all the way up and over the hill. In the case of a catalyst, it sort of finds an alternative pathway, as we'll talk about, for that reaction to take place. But the end result is that's sort of what it does. It kind of lowers that hill. Now, this effect on temperature relationship is what is sometimes referred to as the Arrhenius equation. This is one sort of version of it. We'll see a more kind of natural log version of it, which most commonly is used by people. But this is basically some of our normal stuff. This is our rate constant. A is the frequency factor, and as we'll talk about it, it's sort of the proportion of molecules that have sufficient energy to kind of get up and over that hill to the other side. So that's sort of what the frequency factor is. It's sort of that grouping of molecules that really can get up and over that hill to the other side. E of A is obviously our activation energy. Usually that is in kilojoules. R is our gas constant, and it is the one that involves energy. and T is our temperature here in Kelvin. So this is one version of it. We'll actually see two other versions of it more commonly used than sort of this version. Basically, they come through and take the natural log of everybody that's in there, and we get sort of the more Arrhenius equation that we were sort of used to. And again, here's just sort of that idea of what we were just talking about. These guys are coming, and again, we pretty much got to break all these bonds, start making some new bonds. Again, as it's climbing the hill, we'll hit that sort of activated complex there and sort of come down to the other side. Now, activation energy and the activated complex, as I sort of was talking about earlier, again, is that energy bearer to almost all reactions. And depending on how big or small that hill, as we've been talking about, obviously has a drastic effect on sort of that rate of the reaction. The activated energy is the amount of energy needed to convert really reactants into that sort of activated complex on top of the hill or transition state complex. And again, that is sort of our guy, as we talked about, this very high in energy because it's sort of a transitional sort of guy as we're breaking apart all the bonds and also obviously coming back together and making new bonds on the other side. And here, just a sort of an example of sort of what's happening in sort of the process. I think this will take us through it, I think, if I remember. So we have sort of this guy here. And basically we're going to rearrange and make sort of this. It's really the same thing. We're just sort of moving these bonds and breaking these bonds in this particular example here. As it starts, obviously, there's some bond weakening that's happening here between these guys here, the nitrogen and carbon bond. And again, that's us sort of starting to break some of those bonds as this transition occurs. As it starts going up the hill, as you can see, we're starting to break apart some of those bonds that were holding the molecule together. As it continues up the hill, we got partially broken bonds. We're starting to make some new bonds here as it's starting to try to rearrange and bring the carbon in coming this way. We're breaking those bonds, kind of moving the nitrogen out that way. Again, this sort of partially made and broken bonds that are happening up here on the top, sort of our intermediate. Then it comes down, obviously, and rearranges, as you can see in this particular reaction here. And we get our product that's made on this side. Now, the frequency, again, is that number of molecules that begin to form activated complex in a period of time. That's that frequency factor. Again, it's sort of really that group of molecules that really do have enough energy kind of to get up to the top of the hill there and really start this process. The overall delta H of the reaction here, right, is basically the difference between our reactants and our products, right? So that's where we get our delta H of this reaction is the delta H really of the products minus the delta H of the reactants. But you get this sort of, again, sort of transitioning that's occurring as you come up the hill, bonds starting to break, new bonds starting to make. And in this case, it actually doesn't completely break apart into two new things. It's more of an organic sort of rearrangement. But in a normal reaction at this point, we would have guys kind of breaking apart into maybe two or more sort of products that would be formed as you come back down the hill towards the other side. Any questions on that there? So as I was mentioned before, that sort of Arrhenius equation that we were just looking at does sort of describe the relationship between temperature and sort of this rate of the reaction. And we see that with this graph here. So if we do make a graph of the rate constant versus temperature, we see pretty much what we anticipate here. At very low temperatures, we have kind of a low rate, right? At low temperatures. We increase our temperatures here, a sort of higher temp. We go across. If you want to cross straight, let's try it again. Take two. There we go. We would have a higher rate that happened there in that particular case. So we do see, again, that relationship between temperature and the rate of the reaction. And taking that sort of equation that we saw earlier and really kind of going through with the natural log of that whole equation, we do get more of the version of the Arrhenius equation that we commonly sort of are used to, and it is this version here on the bottom. It's sometimes referred to as maybe the graphical version of the equation. It's the one that's basically written in the form of a straight line. So if we look at that version of that equation there, this is y is equal to mx plus b. By the way, there is a negative. I'll move it over here. So you can see there actually is a negative right there. And if we look at this, this is typically what we would graph. On the y would go the natural log of k. On the x would go 1 over the temperature in Kelvin, and that would actually yield us a straight line. This is very useful sort of version of this equation, because if you look at what the slope equals, now that I threw the negative in there where it should go, it's kind of far away. The slope of this line will equal minus E of A over R. Now, this will allow you to graphically, if you have the right sort of data points, what the activation energy for that particular reaction may be. Any questions on that? So this equation here that I boxed and then just kind of graffitied over here is sort of an important equation. Again, you can definitely use this equation, but most people, when you go with for this guy's equation, this is really kind of the version most people think about, because again, it's kinetics. It has to do with a lot of graphing and stuff that's very commonly done, and kind of linear graphs sort of in kinetics is used a lot. So let's talk a little bit though about sort of that graph. Here's sort of an example of what that graph would look like. And again, you can see it should yield you a straight line. The importance is obviously to make sure your temperature is in Kelvin, and this is the natural log. Now, because the slope here does equal minus E of A over R, and again, I'll just make that minus bigger over here. A couple of important things about the activation energy. First off, when you look at this line is a negative line, which means it's going to give you a negative slope. And that negative right there will turn our activation energy into a positive number. Activation energy should be a positive number. If you think about the graphs we just looked at, right? This is our activation energy. The other graph looks something like this. There we go. This is our sort of activation energy here. And they're both positive, right? It's a hill, which means it does need to be a positive number, basically. So that's something to keep in mind. You should always end up with really a positive number for activation energy. Again, because it's a hill that people got to climb to get to the other side, it's sort of a positive number that always occurs. Other really important things are units. Again, mathematically speaking, when we talk about units, we've seen this in a previous chapter in sort of thermodynamics. Remember, E of A is typically in kilojoules. R is in joules. So again, you got some unit considerations to make sure that you sort of end up in the right units. For example, just to finish it out here, you would take the activation energy here would be minus R times the slope here. And that would give you your activation energy. It actually would give you your activation energy in joules because of R in this particular case. So that's how you do it. And again, with the assumption that your line is going to be negative. So again, that negative and negative will turn your slope or your activation energy into a positive. So looking at this equation just a little bit more, some of the stuff we sort of talked about, but again, just a reminder, that fraction of reactant molecules that really do have enough energy to sort of make it over that energy barrier is sort of that frequency factor. The higher the energy barrier, the larger the activation energy. Again, we would assume that there would be fewer molecules that would have enough energy really, again, under sort of normal conditions to sort of get up and over the hill. So that sort of relationship of how big the hill is to how fast the rate could occur, under normal conditions, we assume large hill, slower reactions, smaller activation hill. kind of a faster reaction. And again, as we talked about, increasing that temperature can definitely get more guys the sufficient amount of energy to sort of overcome that hill. Again, increasing the temperature really is, increasing sort of the energy everybody has, allowing bonds to break and make a little bit easier. Obviously, the opposite is true, as we talked about as well. If we lower that temperature, we're really lowering the number of guys that will end up with sufficient amount of energy to really get to the other side. If you remember earlier, we saw something like, for on average for a lot of reactions, if you sort of increase the temperature by like 10 degrees Celsius, you typically will see like a doubling in sort of the rate of the reaction. Again, not all reactions, but in a lot of reactions. And again, it's just giving everybody more energy, allows them to break apart and get up and over to the other side a lot quicker. And that's what we see here in this sort of diagram here, temperature 1 versus temperature 2. Temperature 1 is there the lower temperature, and temperature 2 is the sort of higher temperature. And when we think about when we get to that activation energy line, if we look at our temperature 1, which is the lower temperature, the amount of molecules that have enough energy basically to get up and over the hill is only that much. But now if we increase the temperature, what we actually then see is the amount of energy needed to make that activation energy, I'll just go next to it here and then kind of curve over, is this amount of molecules now sort of have the amount of energy required to get over there. So we definitely see an increase in the fraction, and if I could draw straight, that would be much better, of molecules that can basically get to the other side by increasing that temperature versus obviously here is sort of where we max out at that lower temperature, a much smaller proportion of molecules able to get to the other side than what we see there at the higher temperature. And that all has to do with really how fast a reaction will take place, right? So this sort of guy at higher temperature, a lot more guys have the energy, a lot more guys will start reacting. We would start seeing products probably being made a lot faster than we would there in the lower temperature. Any questions on that there? Okay, so looking at that equation that we saw earlier here, again, this is a really good equation. It's one that's used a lot, and specifically in sort of graphing purposes. And one more time, this is written as y is equal to mx plus b in terms of our graphing. So, how would you use this sort of information? Let's take a look at sort of an example here. And by the way, in terms of the units as well, we would, the units of A are usually the same as the units of the rate constant. So sometimes people are like, what are the units of the rate constant? And we'll talk about why that is here in just a second. But this would be a typical sort of problem that you would use. Again, this equation that we just talked about, you'd be given a table, for example, of a bunch of information. And in this case, we have temperature values, and we also have rate constant values. They were nice enough here in this table to give us the values in Kelvin. Very common though, you are given the values in Celsius. Remember, you do need to do that conversion here as well if you do want everything to sort of convert correctly. So what would you have to do for each of these? Well, looking at our equation, right, that we were talking about just a minute ago, we know that on the y, we need to graph the natural log of k, which means in each of these columns here, you would need to go through and convert these values into the natural log of k. And those were what it would be plotted on the y points. Obviously here on the x is 1 over the temperature in Kelvin, which means everybody here in Kelvin, since they're already in Kelvin, you would need to take and convert to 1 over the temperature. These will give you several points that you could graph, for example, in a program like Excel or something like that, and do like an XY scatter plot, a best fit line, all that good graphing stuff. Get the equation for the line, and you'll end up with a graph that looks, for example, something like this. This graph is from all those points Again, you can see all the natural log guys have been, or the K guys have been converted to the natural log of K. Our temperature, 1 over temperature, gives us this straight line, pretty straight there. We get our equation here from the actual program that you would graph it, unless you're old school and like paper and pencil and want to graph it that way. I suppose you could do it. But we could use this information to actually answer what the question is asking. And the question here is asking two things. It is asking, what is the activation energy and what is the frequency factor for this reaction based on that information that we got before. So again, looking at our our formula that we've been looking at here, which is our natural log of K, is equal to minus E of A over R, 1 over T plus the natural log of A. Again, our y is equal to mx plus b. So first off, if we want the activation energy, we would want to take the slope value here. So the slope value, again, would equal r minus E of A over r. So our slope equals minus E of A over r. In this case, if we want our E of A, it would equal minus r times the slope, putting our value in, minus r, which is 8.314 joules per Kelvin per mole. Our m from the equation, again, negative 1.12 times 10 to the 4. There's our negative and our negative, which is going to turn our activation energy into a positive number, which is what we want. We'll end up getting us here. We put it in there, 8.314. We will end up with 93116.8. The units here would actually be joules in this case. And again, since activation energy is typically in kilojoules, maybe we'll do a little dividing by 1,000, gets us 93.1 kilojoules in this case, would be the activation energy for this reaction. Any questions on how I calculated that there? Now, the other thing that we're looking for is what is the frequency factor? And the frequency factor is A. And sometimes people miss this little part that it's actually the natural log of A in this case. Sometimes just go, it's A equals B, which is our y-intercept. This is our y-intercept, right? This is y equals mx plus b. So b here would be our y-intercept here. And that means that the natural log of A would equal 26.8. We obviously need to take the E of both sides. And remember, when we do that, the natural log goes away. We get an A that is equal to, call it 4.36 times 10 to the 11. That is a big number of molecules that have sufficient amount of energy to get to their side. What are the units here? Well, again, as mentioned earlier, if we back up to our table, typically the units of K match the units that, the units of A matches the units that we have for K. So this would be 1 over molar seconds would be our units here, which would match. And why is that? Well, essentially, when you take the natural log of A on this side, when you take the natural log of K, the units go away. When you take the E of it, the units come back, basically. And it's the y-intercept, right? So where it crosses y is basically what we're doing. So when we do that E, we get rid of the natural log, brings back the units of K, and that's why they usually have the same units associated with it. Any questions on that? So this is, again, a very common sort of approach, especially experimentally, to determine the activation energy for a reaction. You could simply do a basic kinetics experiment and then do it at a couple of different temperatures, basically get some rates and have some concentrations and get some orders, and you figure out some rate constants, and you can actually do sort of graphical approach to try to determine that activation energy. Any questions on any of those sort of steps there? Now, nobody really wants to graph all that much, and I imagine I probably wouldn't make you do the graph, but maybe I would give you the graph. I don't know. We'll see. So there is sort of a more mathematical approach to the Arrhenius equation that involves temperature. And again, here we can basically sort of mathematically solve for it as long as we got a couple pieces of information, maybe a rate constant and some temperatures, or maybe two temperatures and another rate constant, activation energy. We could also find the activation energy if we know the rate constants and sort of the temperatures. So really this is sort of like if you took that line we just drew and took kind of 2 points that fall along that line, you could kind of use it to solve for certain things. These are a lot of the stuff that we should already kind of know. This is the natural log of K2. So obviously these are rate constants here, right? These are rate constants at two different temperatures. And these obviously would be the temperatures over here. And much like everything else here in chemistry, right? They do need to be in Kelvin. We have our gas constant, which is still our 8.314. We have our activation energy, and we still have some unit issues, especially with this equation here. So much like some other ones that we saw there, you do have to sort of choose. So either, kind of convert the kilojoules to joules or the joules to kilojoules, whichever way you want to do it. There's actually, honestly, there's kind of like three different versions of this equation. Sometimes you'll see the negative from inside sort of factored to the outside, and the negatives on the outside, and then some of these guys change. You also sometimes see a version of this equation where the denominator on the inside is sort of combined, like T1 times T2 and stuff like that. So we'll roll with this version of the equation. But, if you look around, you might be able to see some different versions of it. Might look very similar. Sometimes K1's on top and K2's on top, depending, again, if you kind of distribute out the negative and stuff like that. But we'll kind of roll with this one. So in this version here, natural log of K2 over K1 equals E of A over R, 1 over the temperature in Kelvin minus 1 over the, again, temperature in Kelvin. So again, if you have kind of just 2 points and you want to mathematically sort of solve for it, either the activation energy or any of those other things, you can kind of do that. All right, so why don't we try one here? So why don't you give it a try? We got this reaction, we got some rate constants. We're looking for the activation energy here. So see what you come up with, and then we'll talk about it. Yeah, so let's take a look here and see. So in this case, we do have a rate constant given to us, which is, we'll just call it K1. Why not? Because it comes first. It goes with obviously a temperature, which obviously we will call T1 to match it, which would be 701. Since we call the other one K1, we'll call this guy K2, which is 567. And again, since that rate constant and temperature go together, we want to make sure we do number them sort of correctly in that sense, that they're both the same. We're looking for the activation energy here. So again, we can use sort of our 2-point version. K2 over K1 is equal to E of A over R, 1 over T1 minus 1 over T2. In this particular case, we were good. Like I mentioned earlier, we are both in the same units. So we don't have to do any type of conversion. It's already in Kelvin and the same units on both. So really, you just want to plug in here. So this is going to give me my natural log of K2, which in this case would be 567 divided by my K1, which is 2.57, equals E of A, which is what I'm looking for, again, divided by our gas constant that involves energy, divided by 1 over our T1, which in this case would be 701, minus 1 over our T2, which would be 895 in this case. Any questions on that so far? All right, so I'm going to do a little bit of cleaning up here. We'll start on the left. I want to make sure that I don't mess up like a lot of people do. I actually want to divide what's on the inside first and then take the natural log of it. So if you do that, that is 5.3964, we'll call it, equals E of A over 8.314. I'll also clean up what I got going on in here. So that is 1 divided by 701 minus 1 divided by 895. That's going to give me a lot of zeros, 0.000309. Why not 215? Might as well write all the numbers, suppose. All right, so now I need to do some math, right? So also messed up is people for some reason want to always subtract this number, but we're actually multiplying here, right? So we want to make sure we're multiplying. So we're going to multiply the 8.314 to the other side. We're also going to divide by the number that's 0.0003. So if we do that, we got 5.3, sorry, point, keep 1.1, 5.3964 times 8.314. We're going to hit equals. Then we're going to come back and divide by the 0.00030925. Going to yield us an activation energy of 145,095. These would be joules based off of that. And that would then get us approximately 145 kilojoules is our activation energy. In this case, again, it is positive as well. Any questions on that there? So again, you just want to make sure you don't miss any of those sort of conversions or anything like that, that you end up, getting sort of those units correctly. Any questions on that particular one? Okay, I think we might have one more to go. Yeah, we do. Why don't you give this one a go, and then we'll talk about it. So let's take a look here and see. So in this one, as we were talking about before, and as was mentioned before, again, that idea that if you raise the temperature about 10 degrees Celsius, you typically see the rate sort of double. Again, remember the rate constant sort of determines is sort of like the rate of the reaction. Sort of a larger number is going faster. Obviously, a smaller number is going a little bit slower in terms of the rate. So they didn't really give you temperatures, so they kind of just picked really a 10-degree difference here. There's obviously a 10-degree difference in Celsius as well, right? Celsius difference. Again, if you subtract the 273 off of both of those guys, you end up with 27 and 37, which again is a 10-degree difference. They also didn't give us really values for the rate constant, but we can basically use that relationship. This is basically saying that the rate of the second reaction there at the higher temperature is basically twice the rate at the lower temp, right? That's basically what that means. So we can really kind of put those values in and the temperatures in and solve for activation energy. So if we do that again using our equation here of K2, K1 is equal to E of A over R 1 over T1 minus 1 over T2. 1 over T2. And again, using that relationship that we just saw there on the previous page, that the K2 is twice their K1. Putting those values in, that will give us the natural log of 2 over K1, or 2 times K1 over K1. It gives us our E of A over our R, which is our 8.314 joules per Kelvin per mole, times our 1 over our first temperature there, which was, looks like 300, minus 1 over our second, which was 310. This basically, again, even though we don't know the numbers, they're the same on top and bottom, cancel out, basically gives us the natural log of 2 is equal to E of A over 8.314. Again, if I kind of clean up what I got going on in there, that gives me 1 divided by 300 minus 1 divided by 310. a lot of zeros, 0.00010757. At this point, natural log of 2, as we've seen a number of times, natural log of 2 is that 0.693 number, E of A over 8.314. And of course, our guy over here. Again, mathematically, we want to be careful and make sure that we actually do the correct math moves there. So there is no adding or subtracting here, which again is a common error that people make on this thing. We're multiplying the bottom to the other side, and then we're dividing this guy back over to the other side. So multiply, then divide. So if we do that, natural log of 2, which is our 0.693 times 8.314 divided by our 0.00010757, going to get us about 53,594 activation energy. Again, joules coming from here are really the units. And if we convert that into sort of a usual activation unit, which is kilojoules, we're looking at like 53.6, give or take. Again, positive number here for our activation energy, which is again what it really should be. Any questions on that there? Okay, so I think what we're going to do is we're going to stop